Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to Module 3.1. It's the first module for week 3, and we want to continue where we left off in week 2. As you know, in week 2, we talked about these general equations of quantum transport. And as I mentioned, if you know this H matrix that describes your channel and the sigmas that tell you the connection to the contacts, then you can calculate the current, density of states, electron density, all from this set of equations. And the H, how you write that down, that's what we talked about in week 1. And how the sigmas are written down, I guess what I explained in the last week was how to do 1D problems, where the rule was fairly simple. Namely, the sigmas had all 0 elements, and the only non-zero element was this t e to the power I k a. And so in terms of the method for doing 1D problems, we have discussed it already. So what we want to do this week is, I'll start with 1D example, I guess, where the method is clear, and what we want to do is look at some results and understand the physics. As I've mentioned, with these quantum transport equations, it's important to learn how to use them properly so as to get correct results, and secondly, understand the results. And those two are kind of two separate things. You want to calculate reliably and understand them. So here, the method we are clear on. Now, what we'll discuss is an interesting example that illustrates some very important physics, this wave nature of electrons. Now, the example I have in mind is the following. You see, in the last module of the previous week, we talked about how you can calculate the scattering through a single scatterer. So somewhere if you had a potential U, just one of them, see, then what you'd get when you looked at the transmission would be something like this. And of course, if you did not have any scatterers, then you would have seen something like this. That's the ballistic case. In the ballistic case, transmission would be 1 as long as you are inside the band of energies where states are available, and it's 0 outside. Whereas, once you put a scatterer there, electrons get scattered, there's less current, and so when you plot this transmission, and if you remember, this transmission is something we discussed again in the last week, is basically this quantity. That is, as long as you have two terminal devices, coherent devices, you can write current in this form, and this is the quantity we call transmission, and Q squared over H times that quantity is like the conductance function. Okay. Anyway, so this is the thing where with one scatterer, we expect to see this. Now the question is, what would you see if you had two scatterers? See, a second one, right? So you got, that's just one scatterer, I will call that A, and that gave us this curve. Now you have two of them, you have A and B. Question is, what do you expect to see? And this is where, if you just set this up, set up this set of equations, because once you have set it up for one scatterer, adding another potential, that's very easy. It's just a particular diagonal element, appropriate diagonal element you change. And in your homeworks, I have homework questions. I have also attached my MATLAB code for this. So you're welcome to try it out or write your own codes. Okay. Now, when both of those are present, the result you get is the following. It looks something like this. So what you see is these very sharp peaks. So at a particular energy, there is a peak in the transmission where it actually reaches 1. 1 meaning as if there were no scatterers. It's this ballistic case almost, at that energy. Then comes down, and then again goes up. You see? Now, the first thing I want to stress is how surprising this is from the point of view of particles. That is, if you think of electron as a particle, then you see it's very hard to rationalize this. Because what it is telling us is that if you had this channel with just one scatterer, the way I think of scatterers is, you have this highway and there is this place where it's kind of hard to get around. So maybe like a little toll booth or something where you have to slow down, etc. And naturally that cuts down the traffic. And so you don't quite get as much current as you used to, you get a whole lot less. So that's like one of them. Now what you do is, you come along and elsewhere on the highway, you put another of those little zones, where things slow down. So what common sense tells you is, well, the traffic will get even slower. Well, maybe if you timed it right, it wouldn't change things too much so that once people get out of one, they'll get just in time to get to the other, etc. But there is no way, you see, it could increase. What this calculation is telling you is that at this energy, an electron cannot get through one scatterer, but it can go clean through two scatterers. And so from a particle point of view, from this common sense particle point of view, see, that's really very counterintuitive. On the other hand, in the context of waves, this is actually fairly well known. This really comes from the wave nature of electrons, and it naturally comes out from the set of equations we are talking about, because this set of equations started from the Schrodinger wave equation, which describes the wave properties of electrons. So it's natural that this property comes out. Now, with waves, this is very common in the sense, well, the one example you may be familiar with is what are called these anti-reflection coatings on lenses. That is, if you have a camera and there's this lens, and usually when light hits this lens, there is some amount of reflection. And the way you can eliminate the reflection or make it much lower is by putting a coating on the top, so that there is some reflection from here and there is some reflection from the front surface, and the two reflections cancel out. You see? And if this thickness is just right, actually the thickness has to be usually this quarter of a wavelength. So for whatever light you're using, if this is quarter of a wavelength, if it's just right, it will cancel out. So in other words, here's a case where as long as there was one interface reflecting, there was a lot of reflection, but once you put two of them, they sort of cancel out and let light go clean through. In a way, this is almost what we are talking about with electrons is similar. You had one place that was reflecting the electrons, but then this is like the anti-reflection coating on that one. So you could kind of think of it that way, as if B is the anti-reflection coating for A. Anyway, so the point is that this is a wave property, which is really quite counterintuitive and comes automatically out from our method. Now, how would you understand this? Well, if you start from a wave point of view, then actually it's not too hard, because the way you could argue is the following, that, well, I have a box here. Think of these as big walls, so as if I have a box here. And one of the things I stressed in week 1 is that anytime you take a wave and put it into a box, see, the allowed energies become discrete. And the analogy I had used then was, it's a little bit like a guitar string, that if you have a guitar string, in general, you could have acoustic waves at all kinds of frequencies. But once you pin it down at the two ends, that's when only discrete resonant frequencies are allowed. Why? Because, well, the way we think about it is that the wavelength has to fit into that box. And you could say something similar here. Well, the electron wave has to fit into this box. And that is why inside this box, I have only discrete energies that are allowed, energies around here. And whenever an electron coming in from outside happens to match one of those energies, you go right through it very easily. Around here, around here. Whereas if your energy doesn't match, then you don't get through. So it will be sort of like, I have this guitar string, and I try to excite it with an external source, like a tuning fork. So this guitar string, let's say, is matched at 400 hertz. Has a resonant frequency at 400 hertz. And I come in with a tuning fork that's a little bit off. Well, if it's a little bit off, then it just vibrates a little bit, not much. On the other hand, if my tuning fork matches it precisely, that's when it starts vibrating wildly. You see, and some of you may have done that experiment in a physics lab at some point. So here also is something like that the electron has certain resonant energies. But then you have these electrons coming in from the contacts, trying to get through those levels. And if it matches, then it goes right through nicely. And if it didn't match, then it doesn't get through as well. That would be these regions. So one thing that I ask you to do in one of the homework problems is use this point of view to see if you can understand where those peaks occur. So what you do is you try to find the appropriate wavelength at different energies. So the wavelength of the electron changes at different energies. And the way it is described is, as you know, this E for a box like this is given by this epsilon plus 2t cosine Ka. And the K is what is related to the wavelength. That is, this. You can find the condition for having a resonant energy by saying that K times this length should be a multiple of pi. So that's what I ask you to do in one of the homework problems. And I'll go over it in a tutorial to show you that when you do that, you indeed get approximately the right answers. Not exactly, because this picture assumes you have a perfect box and electrons can't leak out at all. But when you connect it to the surroundings, that also tends to move things a little bit. So you don't expect to get the answer quite right, but you get it approximately right. And that's one thing in general I like to stress with all these calculations is these equations allow you to compute things, but what you should always do is whatever you compute, try to see if you can understand the features of what you compute in common sense terms. You see, that really helps you understand the physics behind all of this. See? Now, the next point that I want to talk about a little bit in this module, and we'll continue with that in the next module, is something like this. Well, is that usually when we discuss the conduction of electrons through conductors, we tend to think of each scatterer as sort of independent. So you say, well, in other words, you think of electrons as particles which have, say, let's say a 90% chance of getting through one scatterer, and then another 90% chance of getting through that scatterer. And then we ask, well, what is the chance of getting through the entire thing? Two of them. And you ignore all this interference between the two scatterers. That's the semi-classical view, you see. And that's the view that actually leads to Ohm's law. In the sense, the reason the resistance of a wire increases with length is simply because there are more scatterers. That is, every wire has impurities in it, which disturb the perfect periodicity. And if you take a wire of that length, you might have, say, 10 of those in it. If you take something twice as long, you'll have 20 of those in it, roughly. And that is why the resistance is twice as much, because you got 20 scatterers, they scatter you twice as much, sort of. On the other hand, what we just discussed is that when you add scatterers, they don't necessarily make the overall reflection any bigger, because after all, one could be acting as an anti-reflection coating for the other. So how do you know? Why is it that we generally see Ohm's law? You see? And this has to do with what are called dephasing processes. That is, in a real solid, you see, often what happens is when I have a conductor like this, we are thinking of this conductor as a perfectly rigid thing. So an electron comes along and all it sees is one potential here and one potential here. And other than that, nothing else. Real solid, especially at room temperature, is really more like a very turbulent medium. That is, here's this electron trying to get through, and here's all these atoms jiggling around. There are other electrons moving around, and so it sees a random potential due to all these other things, you see, which is not quite in this model. And so, often you would not see effects like this. You'd see something that is more like what the semi-classical view would tell you. And this is, again, another thing to be very cautious about. And that is, when you're calculating resistance, you might have a semi-classical model for things. And then someone else might have a quantum model, the model that predicts these interferences. And the question is, who is more correct? And of course, often psychologically you think something that's more complicated, something that you don't understand very well, must be more correct. After all, it sounds profound. Well, but in science, you see, more correct really means what describes the real world better. So you have to compare with experiment and see. And that is where the point I wanted to stress, and this is what we'll talk more about in the next module, is that, this red curve here, there are experiments where you actually see the effect of this. There are things called resonant tunneling diodes, which have been studied extensively because they give rise to very interesting current voltage characteristics, negative differential resistance and all that, which have device applications. So there is a lot of work on resonant tunneling devices, but those have been specially engineered and took a lot of work such that they actually give you this effect. Whereas, if you didn't go to any lengths, and so things were relatively random, etc., a lot of the times what you'd see is what a semi-classical theory would have predicted. And you can see kind of the idea, that is, supposing the way you make resonant tunneling devices usually would be, you have one kind of material here, say X, another material here, Y, and there is an interface right here. And people grow structures like this in the form of thin films, these epitaxial layers, using sophisticated techniques like, say, molecular beam epitaxy. And they see these resonant tunneling effects, this kind of thing. And it gives rise to interesting IV characteristics. But it took a lot of work, actually, to get to the point where you saw large effects. And the reason is, ordinarily what would happen is, these two interfaces wouldn't be quite parallel. This one would have a lot of jiggle to it. This one would have a lot of jiggle to it. And so the distance wouldn't be exactly half a wavelength at any energy, really, because there's a lot of randomness to average over. So these are the kinds of things, you have to be careful about when you're trying to take a quantum model and compare it to real-world experiments. And this kind of thing is generally what you refer to as dephasing processes, things that lead to phase breaking. That is, this idea that, you can have interference if a wave reflected here and a wave reflected here have a certain phase relationship. But on the other hand, if that phase relationship is not quite well defined, that is, changes either with time or spatially, and you're averaging over all that, then you may not see all this. And question is, how would you include such effects into your equations, into your formalism? Because after all, if you want to compare with real experiments, especially at room temperature, you need to include such things. And that's what we'll talk about in the next module. And then after that, we'll go on to discussing two-dimensional problems in general. Because, so far we have only talked about one-dimensional, and some of the more interesting things like conductance quantization, this quantum of conductance, conductance quantization effects are observed clearly when you consider two-dimensional conductance.